1 sir. So you can start.
Okay. A very good afternoon, dear participants. Today we start the next module in this series on HBNI webinars on nuclear science and technology. This module, next 5 lectures will be on applications of radioisotopes in healthcare. And we have a very eminent person today for this series, Dr. N.Ramamoorthy. Dr. Ramamurthy is an expert in radiopharmaceuticals and nuclear medicine. He is from BARC, 15th batch of BARC training school. He has been instrumental in developing many radiopharmaceuticals for diagnosis and therapy, the nuclear medicine area. He was the Associate Director of Isotope Group, BARC, and subsequently became the Chief Executive of Board of Radiation and Isotope Technology, BRIT, which we call it. And later on, took up the important assignment at IAEA as a Director of the Division of Physical and Chemical Sciences. So Dr. Ramamurthy, in fact, has recently written a book also, about which I hope he will talk about, where you can get information about the area that we will be listening to in these lectures. So I hope you will enjoy these lectures and do mark your attendance in the chat box. Over to you, sir.
Thank you, Dr. Tomar, for the kind words of introduction. Dear participants, it's a great pleasure for me to be able to address you all and also give this 5-lecture module on applications of radioisotopes in healthcare. And as we are starting the event on a very auspicious day, April 14, which is the New Year's Day in many parts of India, let me wish you all a very happy New Year as per the Indian system. Some celebrated it yesterday itself. When Dr. Tomar asked me to take this course, I just chose this logo, Atoms for Health, which you see on the slide. That is a slogan from the International Atomic Energy Agency, with which I was associated for a while. It tells it's the role of nuclear techniques in medicine. We are, of course, going to confine ourselves to the role of radioisotopes in healthcare, but a broader one, Atoms for Health, that sounded very appealing. So I thought, let me just put that as the beginning. This is going to be a 5-lecture module, and we will be calling upon a lot of information that had been covered already by in the previous modules by the eminent faculty. Dr. A.V.R. Reddy gave you a talk on the radioactivity, nature of it, the interaction with matter, radiation detection, and so on. That's a very fundamental, important part for the entire healthcare application that we will talk. More importantly, the nuclear reactions and the production of radioisotopes. This were covered by Dr. P.S. Tomar, especially the production of isotopes in his last 2 lectures, L5 and L6. I made it a point to attend that because that gives me the continuity, and I also know what had been already conveyed to you people so that we could build on that line. I do not know how many of you might have attended. There was a virtual event held on the 1st of March, which was to commemorate the 125th anniversary of the discovery of radioactivity. The Vice Chancellor, Dr. Vasudev Rao, made a very important statement there. I thought I should quote it here. History of science is as important as the science itself. This is something very important to remember because lots of things have happened over 50, 60, 70 years, and evolution is a continuous process. Evolution does not mean we forget how very early humble beginnings were made. So I thought I should just sort of remind you that this is the kind of a storytelling of how the radioisotopes are used in the healthcare part. It's essentially linked with the syllabus. So let's recall the syllabus itself. What is the syllabus? Many of you would have taken note of it. It tells about the concept of radiopharmaceuticals, nuclear medicine, then the diagnosis of disease. There are the acronyms SPECT, PET, radioisotopes for therapy, teletherapy, brachytherapy, etc., etc. Keeping the same spirit in mind of the syllabus, what we are going to broadly cover will be as follows in this 5-lecture module. We will have to naturally first delve on the basics and the basis of the applications, the principles, the concepts, what are the radioisotopes, particularly in the healthcare area, etc. This itself, the introductory thing, will complete the first lecture. Then, as the syllabus lays the emphasis predominantly on the nuclear medicine radiopharmaceuticals, nearly 50%, that is 2.5 lectures, will be devoted to that. The other important and probably the more well-known branch to many of you, whose family member, somebody could have had a cancer, therefore they would have taken what is called a radiation treatment. That radiation therapy, that would be coming in the 5th lecture. There are also certain miscellaneous applications beyond this nuclear medicine and radiotherapy, but they are very much relevant in the healthcare area. So we will briefly be touching upon them as part of the lecture 4 at the end of nuclear medicine radiopharmaceuticals. As the world grows, we all know, like, there are the issues, concerns to do with violence, terrorism everywhere, and the nuclear field is no exception. Because of that, there are some security concerns related to certain amount of the radioactive materials. This does affect the healthcare applications a bit. So we will see a little bit about that, not to be left out towards the end. So this is how the syllabus is built within this 5-lecture module. That brings us directly to the very first, that is today's lecture, where we are going to cover the basics of the radioisotopes used in the healthcare, the principles of the applications, as well as the range of applications which are there, and what exactly we may be able to cover in these limited number of lecture modules. So that's the introductory part of it. We get to the radioisotopes. You all know, you have heard already the full lecture on the nuclear structure, instability, which gives rise to unstable isotopes, and they could be giving rise to a certain amount of radioactivity. So the radioisotopes, which are the unstable isotopes of the elements, they become a very, very important tool. But I'm sure somebody would have told you already about radioisotopes. Just to put things at ease, many of you would have already studied a lot, but you know, we are all radioactive. We all carry potassium in our body. And as you know, in the natural potassium, there is one unstable isotope, that is the potassium-40. It is present in a very small percentage, as the slide shows, 0.0117. But if you take an average person, 60, 70 kg person, that means we are carrying something like 15 to 18 milligrams of 40, the radioactive material in our body itself. But that's an extremely small amount of radioactivity. It has a very long half-life. I only gave that example just to put at ease that the concept of radioisotope is something very inherent. We all face it daily. We have it in the air around us. There is a very limited amount of the carbon-14, which is cosmically produced, which is also there in the atmosphere. So those carbon-14 or the potassium are part of our life, part of our human beings like us. So that's the type of a radioisotope which is even naturally present, but they have not very directly helpful beyond a certain point. So there is scope to produce a large number of radioisotopes artificially, and one can use them. And it is in that context that March 1 event, which I mentioned, the 125th year of the discovery commemoration event, Henry Becquerel's discovery, followed by the Curie couple, Madame Marie Curie and Pierre Curie. A large amount of radioactive materials which are naturally present were discovered, and that gave rise to a lot of other isotopes to be looked at. But you know something, like in the topic of the lectures, which is the healthcare, the very early use, more than 120 years back, as soon as they had some natural radioactivity, there was a feeling it could be used for medical purpose. So a radium source was kept near a TB skin lesion, you know, where the tumor is there for a person, the TB is there. That was tried in a very crude manner. Of course, way back, 120 years back, we have to go on. Same way in 1913, a natural radioisotope was injected for studying certain diseases. This is to say the curiosity has been there in the very early days as soon as natural radioactivity itself was found. Many of you might have heard about this professional body, Indian Association of Nuclear Chemists and Allied Scientists. It has a website, encast.org, I think. And there you will find a lot of their bulletins. And one of them, which I call the collector's item, is on the Nobel Prize stories of the people who got it for nuclear sciences. Just shown that books cover page here. I would strongly urge, out of the various things to study, that should be one book which you should take into account, which will give you a lot of information. We are some few slides essentially recalling what had been talked about by Dr. Tomar and earlier perhaps by Dr. Reddy. Tomar, I heard, so I knew he has told you about this. And some more would have been told by Dr. Reddy also. In general, the radioisotopes, the instability comes to do with an excess amount of neutron than in the normal stable element, or a reduced number of neutrons than what is present in the stable element. So correspondingly, we call them neutron-rich radioisotopes. For example, iodine-131. The stable iodine is iodine-127. Compared to that, you have 4 more neutrons in iodine-131. So that we call neutron-rich. The same thing applies to cesium-137. Cesium-133 is the stable one, and you have cesium-137. Just to give an example on the neutron deficient side, you can take the stable cobalt that is containing the mass number 59, whereas cobalt-57 is a radioisotope, and that you can see it has got 2 neutrons less. And that's how the mass number is different. That cobalt-57 is a neutron deficient radioisotope. So the neutron rich, neutron deficient. Then there are also metastable nuclides. Some of them are very important in nuclear medicine, in that sense that they are only metastable. They mostly undergo what is known as isomeric transition to the stable or to the ground state. And that kind of a thing we mark with the word M for metastable. You know, cesium-137 decays barium-137 and then goes stable barium-137. Same way, tin-113, indium-113M, both these isotopes as well as the other one, 99M technetium, Dr. Tomar had mentioned in his talk. I'm sure some of the other people would have also mentioned. So that's very important because this gives rise to the neutron-rich ones will decay by what's known as beta minus. The neutron deficient ones invariably undergo either electron capture or a positron decay, that is the beta plus EC. The metastable nuclides undergo the isomeric transition, that is what is called the IT part of it. And very heavy nuclides, where there is a far in excess neutron to proton ratio, they tend to undergo the alpha decay and therefore alphas. Alpha radioisotopes are useful in medicine. Recently, they have been coming up. But predominant, most of the applications take place with the beta emitting radioisotope part of it. Now, in all the cases of the radioisotopes you saw in the previous slide itself, there are 3 basic fundamental properties. Their unique half-life, the decay mode, how they decay, whether it is alpha, beta, or electron capture isomeric transition, and the energy of radiation associated with that. In terms of the half-life, you have them right from several thousand years, as in the case of carbon-14, to few seconds, like in the case of an isotope written here, krypton-81M or rubidium-82. There are isotopes you have half-lives in a very wide range. This is an inherent natural property. This cannot be influenced by the human beings. Therefore, this is an intrinsic characteristic. So you will have to choose, depending on your actual usage interest, what type of the radioisotope, what kind of a half-life we will be selecting. But half-life concept is extremely important. We are going to see it repeatedly, call reference to it in our later part of the coverage of this topic. In terms of the radiation emitted, I already told you it could be the particulates, alpha particles or beta particles, or it could be electromagnetic electrons. And in some electrons is also possible. We have also about after the electron capture, how a series of either internal conversion electrons or Auger electrons can be emitted. And these electrons will also have a radiation property, and therefore that also have to be recognized. So in terms of using the radioisotopes, we have the decay mode, half-life associated with the energy. And these 3 properties put together, we try use them to whichever purpose we want. In this particular case, we are going to see more about the healthcare applications. What about the energy ranges itself? Like this has a bearing when we will talk about the principle. So that therefore you should keep in mind the order of the energy that we are talking about. You will find either it will be given in kilo electron volts keV or million electron volts MeV part. Alphas in general somewhere between 4 to 8 MeV alpha emissions from most of the radioisotopes which are in some form or the other used in healthcare is available. So that's the alpha energy range. Take the equally low in the case of tritium, where it is less than 20 keV, to carbon 14, which also we call very soft because it is hardly 150 keV. To all the way to yttrium 90, another radioisotope, where it is approximately 2200 keV. So somewhere from less than 20 keV all the way up to 2200 keV, beta energy emissions are available. This will have a purpose. When we talk about the principles of application, we will find that for some application, we need very large beta energy, and for some, we will need medium or low. And therefore, this energy range, again, it's available on the isotopes. But all the required properties may not be available on the same isotope, but a range is available. Therefore, depending on what we are going to do, where we want to use it, we will have to be choosing it. How about the gammas? Gammas, once again, like the beta range, starts from less than 100 keV gamma rays all the way up to 1330 keV for the cobalt 60 isotope. Cobalt 60 is one of the very important isotopes we will be covering, and that has got a very, very high energy gamma emission. To one of the isotope which you have heard already, technetium 99M, it has got 140 keV. So once again, in the gamma, you have from less than 100 keV gamma emission all the way over 1000 keV gamma emissions are available. So depending on how much penetration we want, we will be able to have. You would have also heard about positron. That's an antiparticle which undergoes annihilation with an electron, and the mass is converted into energy, and the annihilation photons, we traditionally tend to call them as equivalent to gammas, but a technical correct name is annihilation photons. Annihilation photon will have 511 keV. This is another very important energy range which is extensively used in the healthcare, and that's something very, very important. So once again, in gammas, you have a range, very low gamma energy to very high, and somewhere in the kind of the middle, this annihilation photon, and which has also got additional properties which makes it very attractive. We will see the part like. Now, conversion electrons. This is an alternate mode to gamma emission. You know, when an excited state, the nuclide comes down to the ground state, it tends to emit gamma, and instead that energy could be used to knock out one of the electrons. And then that electron is called the conversion electron. So those kind of radiations are also present in some of the isotopes. For example, iodine 125, it's another of the iodine isotope 60 days, which has got 27 to 35 keV conversion electrons and Auger electrons. Auger electrons are nothing but the characteristics X-rays undergoing again something equivalent of the internal conversion. And that was discovered by Auger, so therefore we call them the Auger electron. So you have a huge energy range, half-life range, and decay mode. Alphas or betas or pure gamma emitters. These all make the isotopes very helpful for this application. We will just quickly touch on two slides just to recall whatever extensively in two full lectures Dr. Tomar talked to you about. The radioisotopes are produced by utilizing nuclear reactions. For the nuclear reactions, either you need the neutral particle neutron or the charged particle like protons. Where do you get them from? The neutrons are available in the research reactors like Dhruva in our kind, India, Trombay, and also the upgraded Apsara reactor. These are the ones where you produce predominantly neutron-rich radioisotopes. You take a target inside, it resides in the reactor for a few days or so, gets irradiated, it gets activated, comes back, we process them and take it. So this is a very common, very predominant method of large-scale radioisotope production. Dr. Tomer has nicely elucidated to you where you will prefer a reactor, where you will prefer a charged particle. We need isotopes from both the sources for medical applications. That's the reason why we said production source for radioisotopes for healthcare means you need both the reactor and the charged particle accelerators like the cyclic accelerator, cyclotron. They both together give you practically all the important isotopes that one needs to use in healthcare. So it is both are very, very important. Both the channels we have access in India. We have a new cyclotron, medical cyclotron, and commissioned in Calcutta. One more small cyclotron in Pale in BRC's medical unit there that was commissioned about 20 years back. And similar medical-based compact cyclotrons are also available in a number of other centers where it is used for medical purpose. There are more than 20 such. That's what it says. There are many in other sites like. These two become the very predominantly important sources, and the nuclear reactions are either N-gamma, NP, variety, whatever Dr. Tomer has already discussed with you. And in charged particle, even though theoretically you can use protons, deuterons, alphas, predominantly it is the proton reduced which is used for large-scale radioisotope production, which is used in the healthcare sector. We also made a mention in the terms of the radioisotope accessing. Dr. Tomer referred to you about fission products. I had covered you the reactor-related part of it. There you would have learned about the fission reactions. You may hear more from Ms. Roy when she covers the full fuel cycle for you. It's important to know that when the uranium undergoes fission, a very large amount of radioisotopes, which are called the fission products, they are all there in the fuel element. And the fuel elements which are cooled, quite cooled means kept in storage for a pretty long time. Very many short half-life radioisotopes would have decayed. Still, there will be plenty of very useful isotopes there. And one of them is actually cesium-137. Another important one is 90 strontium. Both these isotopes are used in medicine. We will see their applications later. They come from what we call as spent fuel reprocessing stream. Spent fuel reprocessing stream gives you certain important medical isotopes. But there are also, but I told you, you are processing them post very, very large amount of a cooling decay time to let many of the short half-life radioactivities to die away on the spent fuel, because the spent fuel otherwise will be far too radioactive to handle immediately. But what do we do if you want to produce a relatively short half-life isotope, which is only a fission product? Dr. Tomer mentioned to you about one very important isotope there, molybdenum-99. Now that is produced in the fission, and there is great interest in accessing that. For that, what do we do? You take the uranium itself as a target into the reactor. Instead of sodium as a target for sodium-24 production, you are taking uranium itself as the target into the reactor. And following a relatively limited short irradiation, the uranium is literally reprocessed. But here it will not be like spent fuel, a very large amount of radioactivity. It would have been very small. But such things are also done in order to avail of an important isotope like molybdenum-99 for the healthcare. So the two channels of the reactor and the cyclotron, and also the reactor giving rise beyond the normal neutron activation, as we call, creating the fission-produced isotopes also to be made available to us. Now, this is a simple small table just to elaborate more on what Dr. Tomer had already covered to you about the various important isotopes, the target material which goes in, what is the type of the nuclear reaction that takes place. I have just added a column to tell about a brief, the chemical process. You all will remember he taught you about iodine-131, how it is produced from tellurium by what's known as a N-gamma followed by beta decay. Tellurium-130 absorbs the neutron, goes to tellurium-131, decays by beta decay to iodine-131. So your target was tellurium, your final product is iodine-131. So you have to do a chemical separation, and iodine being volatile, a distillation process is used. Suppose you are using a direct N-gamma relation. Again, an isotope which has been mentioned, which is very important medically, is lutetium-177. And for that, you are taking a lutetium target, lutetium in the form of oxide. It undergoes N-gamma and relatively dilute acid if you dissolve, that will give rise to the lutetium in the solution form. You have a radioisotope. What about one example from the cyclotron? The most important isotope there is fluorine 18. Enriched water H2O18 is the target. And following the PN reaction here, the cyclotron, so you are using the proton-induced reaction. PN, the O18 gets converted to F18. And F18 will be available in the form of a fluoride. Therefore, you tend to do a quick anion exchange chromatography to separate that part. We need to remember the chemical processing, purification, final product will have to be compatible with the half-life. Iodine 131 or lutetium 177 both have approximately a 1 week half-life, 8 days and 6.7 days. Gives you a little more comfort in terms of handling processing. What about fluorine 18? It's only 110 minutes. So every minute counts because it is decaying. So you need a much rapid chemical separation system, very quick handling requirements, etc. And the same thing applies to the next isotope, gallium-68, which has an half-life of only 68 minutes, 110 minutes and 68. Once again, some very rapid methods will be needed. There are two important isotopes in medical application, cobalt-60 and iridium. These are not in the chemical form dissolution type or processing. There it will be invariably be metallic pellets or slugs or the targets. Cobalt pellet, iridium pellet or iridium slug or iridium wire, metallic wire. That is what goes as the target. And their half-lives are also long. Cobalt-60 is 5.27 years. Iridium 192 is 74 days. But production is simple, N-gamma reaction. So the post-irradiation, in these cases, the irradiation will be a larger one, prolonged one, like the retrieval, encapsulation, welding them. That is, they will be encapsulated in a stainless steel material, like, and then they would actually be welded, and the sealed sources will be prepared. And this is yet another of the method of the processing part of it. That's why those two are mentioned there, like. And I just wanted to mention what I just explained in the previous slide in terms of the fission. That is, the fission produce isotopes, long-lived ones like strontium-90 or cesium, being recovered from the reprocessing stream of the spent fuel, and short-lived fission product isotope like molybdenum being produced by taking uranium itself as a target. And here, the separations will be extremely complex because these isotopes are present in amongst an ocean of many other isotopes. A very large amount of radioactivity, very high chemical affinity methods will have to be done and used. But such techniques have been developed, they are available, and therefore one is able to access all these isotopes for the various medical applications. Now, we shift to the principles part of it. In the principles part, the very first principle is going to be, again, this was something which was mentioned by Tomar. And I'm sure in the preceding lectures on the agro applications, this would have again come like the radioactivity, the radioisotope being used as a marker, a beacon, a tracer like. That's the kind of thing which is it. It's something like, in a very simple methodology, like to remember, if somebody is using an extremely powerful perfume, you are one of your former teachers or, your sports mentor, if you imagine, he uses a very powerful perfume as his aftershave, like, even when he is coming at a distance, you will be able to get a fragrance of that, like. In the same way here, the radiation can be detected at a distance from the radioisotope. And if you have introduced the radioisotope into the system that you want to study, as for example, what probably would have been mentioned to you in the agricultural applications, the fertilizer uptake. For the fertilizer uptake, we put the fertilizer on the soil. We don't know how much went into the plant, which plants took more. How can you detect it? Can you do some study? This principle, like the radio tracer, can help there. If you will have, instead of the normal phosphate, phosphorus 32 containing radioisotope containing phosphate, that will behave like phosphate. It will go in from the soil into the plant, but it is also containing the P32 radioactivity. So you will be able to detect without having to look for any chemical separation or so, how much radioactivity from the soil has moved into the plant, and in the plant where exactly the radioactivity has gone. So you have traced the pathway of the phosphate that you applied by following the radioactivity of the P32 associated with the phosphate. This is precisely the part of the radio tracer principle. You need to, of course, have the element that you want to study or follow, and it should have an appropriate isotope. I took the example of phosphorus. It's got a nice beta emission, relatively a high energy beta, 1.7 MeV emission, which is easy to detect externally. Therefore, you will be able to see. You can not only just measure, you can also monitor it as a function of time, how long it took for what you applied on the ground to come into the leaf. This is the very typical example which we cite more for ease of understanding, but the same thing you can apply in the case of human beings. For example, we all talk about iodized salt. Iodine is needed for our thyroid. I am taking iodine. Now, whether the iodine that you took, whether it is containing iodine, radioactive, if you put a radioactive iodine a little bit with the regular iodized salt, and if you just give it to the person. Now, because it is iodine, it is going to behave like iodine. It's also having radioactivity, so it will be giving you the signal. So you will be able to show, yes, the iodide I gave, it really went to the thyroid. We are not going to do that. I am giving that as an example principle for the radio tracer. But use radioactive iodine in patients, in human beings, to study their thyroid. That's actually the medical part of the application that comes from this principle that the element and its radioisotope will have the same pathway of movement. So as long as you are able to maintain that integrity, chemical integrity, you will be able to follow. Because you are going to only measure the radioactivity, you will not be able to see anything else inside the system. Therefore, this faithfulness of the chemical element form, the radioisotope tagging together will be extremely important. And this principle is extensively used in all the medical applications, medical imaging part. It comes essentially to do with the very ease of reduction, ease of detection. Not only detection, just counting, not the number. You will also be able to map. You can sort of look at point by point the radioactivity distribution in an organ. Therefore, you are able to actually do a mapping of it. To just example, day back, 1925, one of the naturally occurring isotope, bismuth 214, was injected into one arm, and the radioactivity detector was kept on the other arm, just to see when the radiation reaches, and that gives you the blood circulation. It's obviously a curiosity science study of the very early days, but that turns out to be the very first, perhaps, a radio tracer administered to a person and a study performed like. So that's giving the principle of radiation is easily detectable. I have given it, and therefore I'm calculating now blood circulation time. A kind of imagine go way back in that arrangement. And of course, now we have a much more sophisticated arrangements. We have the radiation detectors, and if you have given a particular isotope, for example, fluoride will go to the bone. So if you have a fluoride along with radioisotope, and then you do a radiation detection, you will be able to get the type of the image shown here, which means the fluoride is there, and therefore the fluorinating activity is seen. And that's actually helping you to do an organ imaging. In this particular instance, it's the bone imaging. The same thing can be done for a thyroid, kidneys, liver, any other organ, as long as you have the right compound which will go to that organ, and you have a radioisotope to be put on the compound. And this is the principle which won actually the Nobel Prize for Professor George Hevesy, but it was not purely an accidental discovery. He had struggled for more than 2 years to separate the radium's decay products. And at that time, the development of the things were not so high to clearly know that when you have had 4 points of the decay chain of the radium, what you call the radium D, will actually be a lead isotope. They all know only it has the decay product radium D, and he could not separate it at all from lead for 2 years. And therefore, he said, I can use this to mark lead, so that to study some lead in the plant biology studies, he could use that. And that principle was the later led to his getting the 1943 Nobel Prize for radio tracer technique. But there is also a nice anecdote story. Stories are always easy to tell the principle. Therefore, I have copy pasted the text of what is available. In short, what it means is when he was staying as a paying guest, PG, in Manchester during those research days, he had a suspicion that his landlady is recycling the old food. So what he did quietly one day at the end of the dinner, like just spiked some radioactive material which he has pinched from the lab into that food and left it. Of course, a small quantity. And 2-3 days back, when he felt the same stew has come to the table, he had that electroscope to detect the gold. It's called the gold leaf electroscope to detect the radiation. He brought it to the table and showed, and then told the lady, "This is the recycled. This is the proof." Of course, she did exclaim, "Oh, miracle!" But then threw him out. Rightly so, because that's what landlady would have done in those grand old days. But just to go to show the principle that there was a tracer study performed by him. It's not the safest study to do. Nobody ate the food, but of course, he had used a very small quantity of radioactivity, as the story goes. But just to tell, this is the genesis of the radio tracer principle, and that has been extensively used in all the biological systems. Like what you would have heard about the plants, the fertilizer uptake or other things, or for that matter, the thyroid function, whether it is fine or not, using the sodium iodide. There are, of course, other methodologies for thyroid function now, but suppose you want to do a bone scanning, fluoride will go to the bone. So you tend to take the fluorinating containing fluoride, then you will be able to see from the administration time how long it takes and how it gets distributed. And these kind of things has become extremely important. And that will be a very large component of the nuclear medicine imaging techniques that we will be talking about in the subsequent talk. The second principle is to do with the radiation energy induced biochemical changes. Depending on the location, deposit, like it could attack the cells and it could damage the DNA by the strand breaking. And this is what is the principle used for the causing cell death, cancerous cell death, and doing the cancer treatment. So a known radiation energy induced biochemical process is what is used very enormously in the entire part of the cancer treatment. Similarly, the same kind of biochemical things, instead of complete cell killing, like it could also sort of inhibit the microbial reproduction. And therefore, you will be able to suppress in the kind of microbial colonies and achieve what we call sterilization. For example, the medical products, devices, which should be sterile, because when you are undergoing an operation, you do not want to get an infection from the knife or the other sutures which are used by the doctors. They will have to be absolutely sterile. And for that purpose, again, the radiation can be used. And that's yet another application for the healthcare part. It is based on the radiation-induced biochemical processes, radiation-induced biochemical process, which is what helps in that manner. There are other applications which some other talks will be covering. In addition to biochemical, you can also bring about chemical processes. The same thing, the radiation, interaction of radiation with matter would have been covered in the earlier talks for the radiation detection principle, as well as for the variety of radiation interaction with the materials. There you produce predominantly free radicals, which can bring about cross-linking and therefore benefit polymerization. And this gives rise to certain superior materials formation possibilities. So the material interest, advanced material interest, can be met by cross-linking brought about by the radiation energy. And this material sometimes do have an application in healthcare. We will just be taking one example later. But just to say, we do use the radiation energy induced biochemical processes as well as chemical processes in achieving a certain desired application for us. This is what would have been already partly covered, as I told, the food product preservation, the disinfestation of the microbes that Dr. N.Ramamoorthy would have talked to you about. There the same principle is used. The energy deposited is used to do the disinfestation of the pests, etc. And later, when Dr. Pant will be talking to you, you will be hearing some more about additional new materials to be made. But as far as our part of the thing is concerned, the cancer treatment and medical product sterilization, these two major applications we're covering on this basis of this particular principle. Like the third principle is what we generally know, like when we undergo X-rays, etc. The attenuation and transmission of radiation. In our body, the bones and the muscles, they have different densities. So there is different level of radiation attenuation. And that's the principle with which we get our X-rays done. And the X-ray, or what you call today, additionally, the further sophisticated computed tomography, CT thing. Like here, the principle is the radiation from the radioisotope or like X-ray is passing through a material which could be animate or inanimate, either human being for an X-ray study, or you imagine an equipment or a concrete, whether it is perfectly homogeneous, fine or not. You can do that because the radiation passes through, the attenuation transmission is going to be influenced by the density of the material that is interposed, its atomic number, what kind of the Z it has got, and the total amount of the mass that you are putting in front of it. You would have seen in the principles of the radioactivity being explained that the alpha rays can be stopped with even a thin sheet of paper. For beta rays, you need little more material. It can penetrate through few of light density materials. And for gammas, you need high material like lead or similar hard materials to attenuate them or trans. That is the same principle which we use in the form of what is known as when you perform a radiography of the equipments. Like it is predominantly used with radioisotopes in the case of industry, but from the healthcare, it is not so much of the radioisotope based radiation, but it is predominantly the X-rays and the electrons. So it's also a very important principle, but relatively they go not from the radioisotope, they come from what we call the machine generated radiation, either X-rays or electrons. They are very strongly used, and that's a very important large branch, what's known as the radiology, either planar X-rays or computed tomography. The RA use there is relatively low, but we have the same attenuation transmission principle only when you do the nuclear medicine imaging also, even within the body. For example, if there will be a very obese patient, certain times, certain of the images may not be extremely good. The same thing applies even to certain anatomical features, like in the case of certain of the females being to be scanned time, like depending on their breast size, there can be additional attenuation also. So the attenuation transmission related part is also helpful in understanding the nuclear medicine imaging. But predominantly, this comes in the industrial radiography, industrial specimen, concretes, machines, structures, etc. That will be getting covered by Dr. Pan. So these three principles over the past 6 slides, what we saw, they underpin almost all the applications of almost all your major needs. Something extremely important, these principles. Our focus, I have tried to keep my text predominantly to the healthcare, but mind it, these are the same principles which are applied as Dr. Arun Sharma would have covered in the previous module, or Dr. Pant may be covering in the later modules. Broadly, these three principles really do the whole thing. Now that we know the principles, this makes you to think of which type of radioisotope for which application. I told you that we have a huge variety of radioisotopes in terms of half-lives, in terms of their decay properties, decay energies. Which one to choose for which? That will be dependent on whatever you heard in the preceding 5-6 slides related to the three principles. First of all, for the healthcare, our idea is going to be which is the radioisotope of element of interest type. We may have some elements of healthcare interest, medical interest, and for that you should have an isotope. For example, here I have just give the example of iron, copper, iodine. Iodine obviously for thyroid. Iron, we know it's a very important element for our body, and iron deficiency leads to a lot of difficulties. But they have not really taken off so much. They can be managed by other methods. But very early on, they were all very naturally the curiosity related, that we could use iron absorption, whether somebody is taking the iron, whether the absorption is adequate or it's all getting excreted out. Yes, you can study with the radioisotope. That interest was there. They did look for a radioisotope of iron also for that. But today that may not be necessary to be done using a radioisotope. You have moved away to using other methodologies. We are not constrained to use, therefore that not go into the picture. But there could be some other interest like today with reference to fluorine. Fluorine is not directly the element of interest except for the bone part, but fluorine can be a mimic for certain amount of organic compounds. Therefore, even if you don't have an element of interest, very close analog you are able to take, we will be able to do. We will also see one example. Potassium, I told you, we carry potassium 40, all of us. We need a potassium isotope for a particular important medical application. But potassium does not have a right half-life energy radiation radioisotope. So we will look for a potassium analog. How do we look for? We look for similar ionic size and charge. Potassium plus and thallus. Thallium is the element and it has both thallus and thallic form. Thallus, that is TL1, very closely mimics potassium in terms of ionic size and charge. So since you have that, you then tend to take it. So firstly, the principle will be the isotope should be of an element of interest or a mimic of an element of interest. That should be the first. Second is in terms of the half-life. Our interest is to do an imaging of an organ. Then you want it to be a very short half-life. That means I am going to use an isotope, give it to a patient, get an image done, and then the job is done. Therefore, we don't want the isotope to be hanging on the patient's body for long. It should get excreted out. Therefore, we will look for a very short half. On the other hand, you are looking for a machine-based, radioisotope-based cancer treatment. You want to send a machine to a hospital and that will give radiation and treat the patient there. You want that machine to be there for long enough to be used for quite some time. Then you are looking for a very long half-life. Just I gave two crude examples. You can have, depending on variety of studies, a huge list. So half-life is extremely important. Compatibility to the nature of application and the particular method of use, we will decide whether I'm looking at a very short half-life or very long half-life. And the list of early on, what I showed you, from the few seconds to few years, all of them have been used in healthcare in one form or the other, again, depending on the particular situation. Now, the decay mode and radiation energy characteristics, how we want to do it. Just now we were talking about, say, doing an organ imaging. If you want to do an organ imaging, you want the radioisotopes radiation to come out of the patient's body and reach your radiation detector. So what would be a better radiation emission there? Gammas will be the better emissions. Gammas or annihilation photons will be a better emission because that will penetrate through the body, reach the detector. Suppose it is beta, it is very likely it will be absorbed within the tissues of the body. Very limited radiation outside may be available for either detecting or for completely mapping the distribution. In organ uptake studies, it is not only just the counting of activity in number of counts, it's also mapping the distribution of the activity. And for that purpose, you do need the penetration. Therefore, we will be looking for gammas for imaging part of it. But suppose you are going to study, as probably Dr. Arun Sharma would have told, a leaf has undertaken all the phosphorus or not, or a stem has taken or not. You may be detecting it by a simple technique called autoradiography. That means you are going to keep a photographic film along with your specimen covered in black sheet. Therefore, the photographic film's darkening is going to take place from the radiation alone. And that autoradiograph, what you get, can be even using the beta. So it all depends on what is the particular purpose. For a bulk of the healthcare part of it, we will be looking for the gammas with reference to the imaging. But what happens if you want to use the same thing for the therapy part of it? There you would like the radiation to be deposited within the short volume area that you require. There, the better one will be the alphas and betas, because alphas, betas have a short range. They are going to deposit all their radiation within a short area. And therefore, for a therapy purpose, if you are going to keep the radioisotope close to the cell which you are going to treat, close to the organ or the tissue being treated, that's what's called the close to treatment area, betas will suffice. But all the isotopes may not be able to be taken very close to that kind of a skin or the tumor. Then what are you going to do? You are going to keep the radiation come from a distance. And when the radiation is coming from a distance, then you need gammas only, even for the therapy purpose of it. We'll be seeing some more of these things as we come to specific examples in the case of the cancer treatment part. So don't have to worry too much if some part of it is not right now sounding to you to be very appealing. The idea is to say, utilizing the basic properties of the radioisotopes and the particular application purpose that we have in mind, we will be able to choose a right type of the radioisotopes for each of these applications. These are all coming from the natural inherent property of the isotope that you cannot change, as I told you. The half-life, the decay mode, the radiation energy, they are fixed intrinsic inherent properties. But we also have practical consideration. All that may be there in a nice isotope. How do I produce it? How can I make it widely available? And will it be cost effective or will it be a very huge cost? So these considerations are also extremely important. Can I produce that isotope? For example, we talked about cobalt. And in India, we are lucky we can produce. But there are many other countries where they don't have that. And then they have to import or buy. As you know, anything to be imported, bought will be more expensive than what you produce locally. And those people may have to pay a higher price for that. But availability, yes, because it has got a 5-year half-life, you can always produce and distribute. What about some other isotope like 1 hour or 2 hour half-life? That naturally will have to be produced in a widespread manner because you may not be able to transport it beyond 1 or 2 hour travel time, and therefore you will need. So this supply chain logistics, as we call production methodology, the production volumes being compatible to whatever application you need. Suppose you need an isotope in Curie quantities and you can only produce it in microcurie or millicurie method. It's not going to be done. Production technology. It is the quantity of production. Remember, they did repeatedly on this. Very nice a cycle. Some you have to do and some every day, and sometimes even multiple times every day. Fluorine 18 is one isotope, 110 minutes, and it's very important. So every day, as we are talking, somebody is producing it. That's the kind of the frequency which will come, and that also impacts the thing. So if somebody features available, match it also with whether I can produce or not, then you get the particular isotope. Then we will be seeing in the subsequent lectures about the certain of the applications. We will be repeatedly coming back. It's all a very good, very beautiful isotope, but a production problem. In another case, it can be easily produced, it is available. So let us find some utility for it because it may not be fitting in any of the other requirements with reference to utility. So you find an innovative way because isotope is easily producible in large quantity. Both the examples type will be there, which we will be covering. Now, a bit of the range of the applications are what we are going to talk about. Like, as I first mentioned, amongst the, I do not know how many of you have signed in today, assuming 30 to 40 people are there, we are talking about 30, 40 families. I am pretty sure at least in a few of them, they would have had some patient, cancer patient in the family who would have received or will require a radiation treatment. This word would have been used. So many people know that radioisotope or radiation related to cancer treatment. This is something, even in different families, people need not have studied science. They would have heard about it, it would be available. Whereas the second, which is the larger scope of our syllabus, it's what's known as the nuclear medicine. And it always goes with the conjunctive word radiopharmaceuticals. Radiopharmaceuticals, as the word means, radioactive pharmaceuticals. This is what we are going to cover. That's the syllabus focus. So that comes to be from the next lecture, L2 onwards, part of L4, it will go. And that's the very, very large part. And also, it's a multidisciplinary, multi-speciality. It involves chemistry, physics, biology, electronics, You name it and you have all of them. Like, not that the radiation therapy is any simple. It's also complicated, but it's relatively more of a physical process. Like, whereas here it involves a tremendous amount of biochemical process. There the treatment takes place to do with biochemistry, but in terms of the operation of the machine itself or the practices, procedures, it's more of a physical process. Whereas in the other case of the nuclear medicine radiopharmaceuticals, it is a very complex multi-disciplinary expertise part. I mentioned to you about the radiology X-ray part, which is not from radioisotope, therefore we will not be covering it. We will very briefly touch upon the medical product sterilization using the radiation arrangement, and radioisotope tracer probe can also help in certain other areas like drug development research. There was a field called radioimmunoassay. We will very briefly just mention. Having mentioned it, I also told you that there are concerns about the security of the radioactive sources because they are kind of could be misused by some miscreant for bad purposes. So they have to be protected. When you need a certain things for a very precious application, we need to take care that that kind of a security lapse will not be there, and therefore we will touch very briefly on those things. So that makes the 5-lecture module. But prior to that, a word about our Indian standing and why we are doing all this and talking. Thanks to Dr. Homi Jahangir Baba, we have had a very vibrant program from very early days. Practically in the world, whenever they started almost the isotope program, virtually within years, in India also, we have had a radioisotope program. That's the very big important difference compared to many other countries, which all started much, much later. That came because we had in 1956 itself Apsara reactor, then the Cyrus reactor. In the reactors, you have radioisotope production program, and medical applications was immediately one of the part of the usage. Therefore, BRC and its predecessor, what is known as the Atomic Energy Establishment, Trombay AET, they have more than a 60-year record there. And the Board of Radiation and Isotope Technology, BRIT, Dr. Thromer mentioned it, as currently the responsible one for all the isotope program that has got completed over 30 years. That's been something. We also have the Memorial capital medical application, also application for it under the DAE wing, and there is a radiation medicine center of the DAE which is functioning since 1963. They support all the medical part of the application, the HR development, and the other related things on the application side, and the BRC BRIT part takes care of the radioisotope based products and the equipment side. And I already mentioned in the very first isotope production slide about the cyclotrons today being more than 20 plus in that. So it's thanks to Dr. Homi Baba's vision and the Department of Atomic Energy, the radioisotope program had been vibrant, and whatever healthcare applications we are going to talk about, they have not been alien to our country, and they have been available since very early on. Almost as the field grew, as the application started, India has had the benefit of being able to use them like it. I mentioned to you how it is going to be the structure part of it, just for the sake of the completion of the lecture and to remind, and assuming somebody didn't attend the very first part of my lecture, just to remember, we are completing the basics, basis, principle, concepts, etc. The introductory talk today, which I'll be just now concluding in the next minute or so. And the next 2.5 lectures will go on the nuclear medicine, radiopharmaceutical part. And the other half will be for the other miscellaneous applications. And the final lecture will be on the radiation oncology and radiotherapy. I have tried to keep within this around 18 to 20 slides in every one of the part of it. And I am also putting my email. I know some of you may have put some questions in the chat box, which I am sure the host would have also noticed and informed me. I will also try to clear the full screen mode. I may be able to see. I would stop here as the end of the first lecture. And as I said, this has been an introductory one to build up the case with reference to all the applications. Thank you all for your attention, and I am available for any questions either now or through email. Thank you.
Thank you, Dr. Ramamurthy, for very excellent presentation. I think questions are coming up here. First question is, All of the radio diagnosis methods using the radioisotopes involves radiological exposure to the patients. Thus, the assessment of radiological impact is carried out before the procedure.
You would read out a few questions, or we take one after the other?
Yeah, this is the first question, which is on the chat
Okay.
box. So all
Yeah.
of the radio diagnosis methods using the radioisotopes involve radiological exposure to the patients. Thus, the assessment of radiological impact is carried out before the procedure.
Yeah, good. A good question. In fact, we will be discussing this more in greater detail. Basically, the medical radiation exposure is a situation in which the assessed benefit to the patient management is expected to be high enough to expose the patient to that particular level of the radiation. It's like our going for a X-ray picture. For example, even a normal hale and healthy one, like when somebody has to say medical exam, we are subjected to a chest X-ray. These days, it's being questioned whether it is radiation, which is not expected to create any kind of a significant. That same principle applies in the case of any medical exposure also, but the medical decision making is the prerogative of the clinician addressing, like under the, of course, the opinion of the, a specialist experts there, like they have for all the standard procedures, a very clearly known what will be the approximate amount of the radiation exposure. I will tell you for a diagnostic one, predominantly or very roughly, you can say somewhere between 2 to 10 or 2 to 12 millisievert will be the kind of the radiation exposure. As many of you or some of you will know, what we get in the natural radiation exposure when we are not having any radioactive work also, like, is about 2.4 millisievert per annum. So what one of the medical procedure gives you will be in the order of between 2 to 5 years equivalent coming in that one procedure. Just to give you an idea of the quantum of the number, like essentially the decision is of a clinical nature, whether the benefit of the information obtained is going to be of high value to subject the patient to the particular technique. That's how it is done. Like, it's not like, before or after. The patient has an inherent problem and a certain decision making is dependent, then that radiation exposure is allowed and done. And overall, in any of the procedures, none of them are like in any criticality levels. Like, that's in the diagnostic part of it. The therapy part, it is always a proven patient who is having a cancer known, and it's sitting there and it's known clearly, evidence-wise seen. And therefore, when you are treating, there is a definitively a higher level of a radiation given in that case. Thank you.
Any other question? So I think there are no questions. You can still write to me or to Dr. Ramamoorthy by email. I'm sure we'll be able to answer these questions. So I think we close it here. Thank you for your participation, and thank you, Dr. Ramamoorthy.
Thank you. Thank you.
Bye.
The lectures
Bye-bye.
are interrelated and interlinked. So somebody had felt a question to come up the next time. It's absolutely welcome. It's not that it has to be linked only to what we talked on that day. And the lecture materials will be available after the lecture is over. As per the standard procedure, HBNI will be making available. And if some of you have not particularly attended Dr. Thomas' lecture, I would encourage you to visit his talk slides to learn a bit more, so that it would be helpful, because I will be back and forth referring to it. Thank you.
Okay, thank you. Bye-bye.
Bye. Thank you. Thanks.